Okay, so it's been a starting time now, and so far no students are here, so I'm just going to go ahead and initialize our chat today. So I just wanted to go over a couple of here. Hello, Drew. How are you? All right. So I just brought the screen up to let you know on the assignments that are coming up. So I have posted a couple of additional assignments in addition to the midterm exams. So the midterm exam is due on the 9th. And today I'll spend some time mm, on a few topics that are related to the midterm exam. So there's still some time to complete it. We have a few days. In addition to that, you would notice that the discussion board assignment next week, DV6 and DV7, are due on the same date. And this is for the reason to sort of catch up uh, since we had the holiday break recently. And I didn't want you to work on basically do school work while you're away from on the holiday. So therefore, we just have to catch up. So it's one additional discussion, which is going to be basically next week. You're due for two discussion assignments. The other two assignments that I've posted are essentially the week 8 IP and week 7 IP, which essentially are due on the same week, just before our second break that is coming up for the Christmas. So I just extended the due dates for them just to catch up on the material that I want to cover. So one of these assignments is a lab assignment for which in the second session this week, we'll go over the lab requirements. We will perform some tests and hopefully we'll work on it together so that, if there are any issues in using the tool, that is clarified. And just for information, we're going to be using the Multisim Live. So Multisim Live also has, in addition to digital circuits, you can use it for circuit analysis also here in this course. The other assignment, which is due on the 24th, is going to be also, it's basically a homework assignment. It's homework number 4. And this assignment will be covering the material that we're going to be covering in the next couple of weeks. So you should be able to get up to date on that. And after that, we'll have one other assignment, which is going to be after the break, and one exam. So that's sort of the final exam. So that's just looking ahead. So I wanted to go over that. Now, for from the perspective of exam, I wanted to cover one additional topic, and then I'll spend some time reviewing some of the material that we've covered, which is relevant to the midterm exam. And you have questions, we can have a more interactive discussion on that. So one type of circuit that you may see, for example, so you may have seen a circuit like this. Let's say, let's just assign some values to it. So for example, if this is 50 ohm, 50 ohm, and it says 10 volts. So if I ask you to find the equivalent resistance of this circuit, just by observation, it will be difficult just to see that, you could see that none of these circuits are in either parallel or series, right? So definition of a parallel combination is that the resistors must be connected between the same two nodes, right? The series is that one of the nodes must be shared and in a loop format. So and the node must be exclusively shared. So that node cannot be shared by any other component. So if I look at these, so we have a few nodes here. So let's look at this node. Let's look at this node. So we have a total of 4 nodes in this circuit, and every one of these 4 nodes has at least 3 branches connected to it. So that really throws out the series combination of any of these resistors. So essentially, none of them are in series with one another. The other choice is for the parallel combination. So if I look at the parallel combinations, then so for example, if we look at any of the resistors, none of the resistors share the same 2 nodes on each side. Just as an example, the top 50 ohm resistor here is connected to these 2 nodes. Let's call them so it is connected to A and C, but then if you look at it, no other resistor would share A and C as the connection points. So I mean, that's really a situation where we cannot use the techniques that we know so far. So we have another technique which helps us in this situation, and that is called a Y to delta conversion. So this is, and this conversion can be in opposite direction also. And this specific formula for that, and I'll discuss that shortly. This is also known as T to pi conversion, which is essentially the same thing, is just the way you view it. So if you look at this circuit, so it looks like a T. So a T or a Y are essentially the same thing. So if you were, so we want to convert this into a delta or a pi setup. And when we do that, then we should be able to solve this problem. So let's take a look at how these formula, and I'll just give you a general form. And from that general form, then you can, apply it to this circuit. So let's take a look at this general form that we have, let me change the color so that it's a little bit distinct. So let's label these. Let's call this. Okay. So the general formula, when we are doing, for example, the delta to y conversion, or pi to t conversion, is this. Okay, so that's the formula. So you will have to look at, for example, if I were to look at R1, so what are the adjacent branches? So for R1, like this is R1, so the two adjacent branches are these two, right? So for R1, when I'm trying to find from the delta, and okay, so this is for my R1. Now for my R2, again, if you view R2, the two adjacent branches on either side are RA and RC in the delta combination, since we're converting from delta to Y. So we have to write that. Okay. And finally, for R3, since you can view it from here, the adjacent branches in the delta setup are RA and RB, and RA plus RB, RC are going to be your. So that's how you will convert a delta to Y. Now, if I were to do the Y to delta conversion, so the general form for that is, so you will take the sum of all the product pairs that are available in the Y. So we can say so in the Y network, all the product pairs, we take the sum of it, and then what we do is we the opposite resistor value is taken in the denominator. So okay, so which one is opposite? So let's take a look at it. So if I were to find R sub A, then essentially the three pairs are going to be R1 multiplied by R2 plus R2 multiplied by R3 plus R1 multiplied by R3. Okay, so these are the three pairs that I have. So I'll write those first. So I have R1 multiplied by R2 plus R2 multiplied by R3 plus R1 multiplied by R sub 3. Now, this is the resistor I'm evaluating at the moment. So I'm trying to determine its value. And the opposite Y resistor is just, just you could see that, through this node, R1 is the opposite value here. Okay, so you will have to write it like that. In fact, I mean, I've written it very symmetrically in terms of ABC being the first three letters and 1, 2, 3 being the first three numbers. So I've written it with symmetry, but even if you're out of symmetry, if you remember these two, or you write it somewhere, these two formulas, you should be able to determine what these values. So we just have to look at the opposite direction. Similarly, for RB, the opposite one is going to be R2. For RC, the opposite resistor is going to be R3. So the numerator is going to be same, just like the denominator and the other conversion is the same. So let's go ahead and write the other three combinations. So since the numerator is the same, I'll just rewrite it here. And this is going to be R2. That's the opposite one we determined. And similarly, R sub C is and this is R sub 3. So you need to know these formulas or have access to it in order to do this conversion. So just use it as your notes. Now going back to the problem that we have. So we have let me just rewrite it here and then we do the conversion. So we have a 10-volt power source. And we determined that we cannot do the equivalent resistance of determine the equivalent resistance for the circuit due to obvious reasons. So now we want to do conversion and see if that helps us. Okay, so if I were to convert this Y into a delta, the stop resistor will remain the same. And my power source is going to be there. Okay, this is a 10-volt source. Okay, and we also have this one resistor which is out of the Y network. So when we are doing the delta conversion, the Y is going to be converted to a delta like that. Okay, and we don't know the values of we know the value of these two resistors, but we don't know the values of the other three resistors. So let's go ahead and determine these values based on the formulas. Since it's a relatively same, all three resistors have the same value, so it's relatively easy for us to determine that. So if you look at the Y to delta conversion, the resistance value is going to be, I'm just plugging in values into this formula. Since all resistances are 50 ohms, so for example, if I were to determine the value for this resistor, and the corresponding opposite value is this one, and the other three are there. So therefore, since the value is same for all resistors, it doesn't really matter. It makes it a little easier problem. So then we can add these three products. Okay, so we can rewrite it as 150 ohm, 150 ohm, and 150 ohm. Now let's see if it helps us proceed with the the simplification of this circuit. So if I look at these two resistors, now they're sharing the same two nodes. So let's label these nodes also. Let's say this is my node number 1, this is my node number 2, and essentially there are no components in between. So this is my node number 3. Okay, this is all single node. So if you see these 50 and 150 ohm resistors at the top, they share node number 1 and 2. Similarly, between node number 2 and 3, we have another 50 and 150 ohm resistance. So these two resistors can then be, you take the parallel of them, and the simplified circuit will look like this. We have a voltage source here. We have to account for this resistor. Okay, so this one is 150 ohm, 10-volt source, and this is the parallel combination of 50 and 150, and this is also the parallel combination of 50 and 150. So let's see what that is. So 1 over R equivalent, so being these two, we have 1 over 50 plus 1 over 150. So we have 1 over R equivalent. I take a common denominator as 150 here. So 3 times 150, 3 times 50 is 150. And 1 times 150 is 150. So therefore, I get is 4 over 150. If I do the cross multiplication, I get 4R equivalent is equal to 150. And then R equivalent is going to be 150 or 4. And if you do the math, it's going to be 37.5 ohms. So these are two 37.5 ohm resistors. And now they are sharing a node exclusively, right? So there's no other branch at this node. So that means that these two are in series, so which really converts this circuit to this form.
Can I slow you down for a second? Where did you get?
Yep.
When you got 1 over REQ equals 1 over 50 plus 1 over 150, where did you get that? And then you went from 3 plus 1 equals 150.
Okay, I'll explain that. So if you
I think I got it, but I need a little bit more.
Sure, no problem. Let's refresh that, right? So when we talked about, if you go back to our discussion on the resistor combinations in parallel and series. So in series, what we do is we just simply add the resistance values, and that's our equivalent resistance. In parallel, we determined that there is current going through different branches, and the relationship of current is I is equal to V over R, right? And if you remember, in parallel branches, the voltage is the same. So let's say if I have I1, which is this, and I2, which is this. Again, this could be, I'll try to fit it into this little space. So let's say if I have these two resistors in parallel, and I want to determine the the equivalent values of these. So from where we derive it is this, that
I guess I understand, like when you add resistance in parallel,
okay,
it adds 1 over the resistance amount, as opposed to series, you're just adding it up.
Right.
So I understand the difference between series and parallel.
That's good. So I'll proceed from there. Essentially, what we're doing is we're adding conductances to determine equivalent conductance. The conductance is the reciprocal of resistance. So that's where this came from. Now, how do we get this 4 and 3? Is that whenever I mean, that's not a unique way you can do it. You can solve it in a different way by just taking 1 divided by 50 and then add it to 1 divided by 150, and then take the reciprocal of that. That's going to give you the same result. But in this technique, and normally what we use in math, is that we look for the two denominators, and we are taking a common factor as our denominator. So we see that we take that number which is divisible by both of these denominators. We take that as a common value. So if you look at this, 150 is divisible by 150, and 150 is divisible by 50. Now you could have something else, like, for example, you could have 1 over 3 plus 1 over 5. In that case, it's not going to be very straightforward. what you will do then is you look for the next, basically you look for the smallest common value, which is divisible by either one of the two.
Okay, no, I got it. Yeah, I understand where you got the 3 from. You were trying to get the common denominator. So you
Right,
multiply
right.
both sides by 3.
Correct.
Okay.
Yeah. So I did essentially that, and then one came because that is 150 has equal to 150 is divisible by 150. So I it's just I took that common number there. So then 3 plus 1 came from there.
Okay, no,
Alternative
I get it.
Okay.
Yeah, I
Yeah.
just saw that 3 in there, like, where'd the 3 come from? Because
Yeah.
I get it.
Yeah, so I should have explained it. Yeah, but so you get this 4 by 150, and then essentially you get this number from there. Okay. All right. So let me just erase some of these. As I was trying to write a circuit there. Okay. So now you can think about this. So we combine this. Now this is 150 ohm here. And these two, when added together, is 37.5 plus 37.5 is equal to 75 ohm. So this resistor is going to be 75 ohm at the top. And the other one is 150. So now we do the same thing again. This time we take the equivalent resistance. So we do R equivalent with 1 over 75 plus 1 over 150. So this time I take 150 as a common factor, as a common denominator, and the factors of that are 2 for 75 and 1 for 150. So this time I have 3 over 150. So essentially this is 1 over R equivalent is equal to 3 over 150. I do cross multiplication and I get 3 R equivalent is equal to 150. And this can then be written as R equivalent is equal to 150 over 3, which is 50 ohms. Okay, so this is one technique in which you can, if you see that a circuit is sort of you can't go either series or parallel, then there definitely is going to be a delta Y type of conversion opportunity there. So in this case, we were able to simplify the circuits from a Y. There was a Y branch in the middle, and we converted to delta, which allowed us to do some parallel combinations and simplify the circuit in this way. So in this way, you can resolve some problems like that. Okay. Now, just you have to remember these formulas and this sort of sketch for the parallel, the delta and Y connections. Okay. The other techniques that are going to be helpful in our midterm exam are current division and voltage division.
So the answer to your example is 50 ohms?
50 ohms, yes.
Okay.
Yeah. So we were able to simplify it to 50 ohm. That's the equivalent resistance for this circuit. Okay. So in voltage division, as you recall, we may have some source like this. And if I were to find, this is my R1, this is my R2. This is V1, V2. So essentially you can find your V1 by taking the source voltage multiplied by the relevant resistor over the equivalent resistance, which is the sum of these two. So that's going to be your V1 and V2. So V2 is the same way. This time only the difference is going to be your resistance, corresponding resistor is going to be different. Okay, so that's the voltage division. So you need to remember to be able to use this technique here, okay, in the exam. The other one is the current division. So remember, in the current division, we said that we may have a current source or some current coming in, and that is distributed among parallel branches. So let's just say this is I sub S, this is R1, and this is R2. So if we say that this is I1 and this one is I2, how do we find that? So for I1, we said that we have to take the source current and multiply this by the reciprocal or the conductance value of R1, and in the denominator I have the equivalent conductance of the two. Okay, so that's going to be my current division formula. So for I2, I do it similarly. Sorry, this is I sub S. And conductance of the second resistor, which is corresponding to that current, over the equivalent conductance. Okay, so that's how you will determine the current division. Other techniques that you will use in order to solve the exam are the okay, so you may need to combine resistors that are connected in parallel, or if they are connected in series. And we have, just went through an example which, discussed these two techniques in detail. So, but again, just a general formula for equivalent resistances is the reciprocal of equivalent is equal to all the resistors that you are taking in parallel. So then you can combine it in such a way, and you don't have to really use one technique over the other. For example, if you are given some values and you don't feel comfortable with this common denominator technique, and let's say if I have 1/2 plus 1/5, let's say these are the two resistance values. So all you can do is just simply take these values and take the actual numerical value of this. So 1/2 is 0.5 and 1/5 is 0.2. So we can then say it's 0.7. So in other words, 1/R equivalent is equal to 0.7. So if I do my cross multiplication there, it's going to be 0.7 R equivalent is equal to 1, since there's a implied 1 in the denominator. So 1, and then that R equivalent value can then be determined from there, which is going to be 1 divided by 0.7. So I mean, if you feel comfortable with this technique, you can use that. result is going to be the same, right? Either way you go through it. So I will accept both techniques. Of course, the resistors in series is just the sum of those resistors, so that's really pretty straightforward there. That could also be required for you to solve in the exam. The one other thing that maybe, which actually I see is required, is the source transformation. Okay, so what is source transformation? We talked about source transformation, that if I have a voltage source in series with a resistor, let's just call it source resistor. And in the next topic, next topic that we'll be discussing in the course, you would know that you need to have a source resistor along with it. So there's always going to be you will not see for most practical modeling, you would not see an ideal voltage source because it has its limitations. So we need to have a series resistor with it. In this case, this is the way our practical voltage source is described. And if I were to convert it into a current source, again, this conversion can take place either way. What you will do is the polarity and the arrow has a direct correlation. So the arrow is always going to be pointing in the direction in which the positive sign of the positive terminal of the battery is. So in this case, the positive terminal of the battery is at the top. So the arrow in your current source is going to be pointing to the top. If the positive terminal was at the bottom and negative was on the top, then the arrow would be pointing downwards. So that is something we will do like that. So this is my current source, but we also need to account for this source resistor, which is going to be then brought into parallel with the current. So essentially they are the same. So you can convert from one type of source to another type of source. So current source can be converted to a voltage source can be converted into current source, and you just simply have to apply Ohm's law to determine the values of these. So if I were to convert a voltage source, what I will do is the current source value is going to be determined by this formula. So which is Ohm's law, V is equal to IR. I brought into the current form. So in this case, your current source value will be derived from the value of the voltage source and the resistor. The source resistor value is going to be identical in both cases. So for example, if I had a 10 volt source and a 5 ohm source resistor, then the current source value is going to be derived like that. So it's going to be 2 amperes, and this is still going to be 5 ohms. Okay, so just very simple calculations, but it does help you simplify a lot of things in more complex circuits where you may have multiple sources. So it can help you combine, let's say if you have a current source and a voltage source, you can convert one of the sources to make it, let's say the current source can be converted to voltage source. So then you will have 2 voltage sources, and then you can take equivalent value of that voltage source. If you can make it into a series voltage sources, then you will do that. If you can make it into a parallel current sources so that they are connected in parallel, then they can be added depending on what the directions are. So again, voltage sources in series get added together. Current sources in parallel get added together. And always remember, of course, since you have a lot of, if you have practical background, I remember you mentioned in your um, introduction that you have some military background. So I'm not sure if you did something related to electrical work in the military, but you know that you can never combine two voltage sources of different values in parallel. They need to be of the same value. But if they're in series, then they get added together. Same thing with the current. You can never combine two current sources of different values, in series, because it's not going to be consistent. So that's sort of, with that background, you will have to consider when you're doing your conversions from one form to the other, and that's going to be a useful technique. So one point there that I would like to make is that, let's say you have some voltage source, and let's say there is a I think there's a similar problem on this exam, where you're asked to find the value of a particular voltage. So let's say this is V1. So one simple rule that you can, or I mean, just observation, I would say, not really a rule, is that this V1 voltage is across this particular, so let's say these are resistors, have some values. So R3, we know that the V1 is across R3. And if you're asked to find V1 also, I mean, if this is the question, then you will try to keep the integrity of R3 separate when you are doing the, your combinations, just to simplify your circuit. Now, in this case, if you see, you have these two resistors that are in parallel, and these two resistors are in series, and then there's a series combination of these two together. So you can combine them, but you don't want to take this R3 into this equation. The reason being, then you would lose the ability to determine the value of V1. So here you can essentially combine these resistors, can do the source transformation, convert it into a so what you will have then is something like this. And you would know the value of this I sub s, right? So you know the value there, and from there you can use the technique of current division to be able to find what current flows through this R3, and that will help you find the value of V1. So I mean, there's no unique way of solving the problem. Sometimes you will have abundance of techniques to solve a problem. You just have to, trust in that technique and be able to resolve that problem that way. So I will leave it up to your judgment. So sometimes, just like we use the mesh analysis and node analysis to find different unknown quantities within the circuit, but any circuit could be just like we saw in the last lecture, where you want to look for a simpler application. So if you see that, okay, I'm getting only a single equation through nodal analysis, and I'm getting two equations and two unknowns versus one equation, one unknown. So it's less work to go through the one equation, one unknown. So you just have to spend a couple of minutes just to observe it, unless it's specified. If it's specified that, okay, you have to use a particular technique, then of course you don't have a choice. But if that restriction is not there, and you have the ability to use either of the techniques available, then you will choose that. So we can find quantities using current division, voltage division, mesh analysis, nodal analysis. So all techniques are available to us. You just have to see, just have to be able to apply them. So that's sort of what I wanted to share with you regarding the exam, just sort of a review session. And I can answer any questions. I mean, we won't specifically talk about how to solve the problem, but again, if there's some question about any of the problems within the exam, I can sort of give you some explanation if anything is unclear, because sometimes in the homework assignments you have some areas that are unclear. So I mean, now is going to be a good opportunity to discuss.
Well, so like you have a symbol where you have a plus and a minus, right? That's a voltage source. But then you have a circle with an arrow. That's basically a resistor that's directional.
No. This is essentially what we use it as a current source. Okay, so normally it is just a representation of some current flowing in that branch, and that can then be distributed into further. So we don't have a resistance, but it's just that we can say, like, let's say there is some
So it's current, like amps, not voltage
it's amps,
or resistance,
exactly.
like ohms. Okay.
Yes. So this is some current that is coming from some unknown area, and then it is connected to this network of resistors. Of course, at this point, we're just simply simplifying it into resistors, current, and voltage. So those are the three quantities that we're going to be evaluating. Of course, when you go to circuits 2, then you will be talking about capacitance and inductance, also the reactive loads. So here, this is more sort of linear circuits with only resistors in them. So you can consider this as a current that is coming through. So it will have some value assigned to it. The voltage source, you can just consider just like it's a battery connected, and it is generating some current based on whatever load is connected to it. So the current that is generated by the voltage source will be dependent on whatever type of load. So if you have more resistors, the current is going to be smaller. If you have less resistance, the current is going to be larger. So that's how that is determined. So that's basically the arrow is. I mean, there is also another device that looks like this, and this is a variable resistor, which simply is a resistor with the arrow through it. So it's a potentiometer for which you can change, you can tweak the values. So at some point you may be able to use it in future, but for our purpose, we are not really. I mean, some of the problems are worded that way, where it says that, what if you change the value of a resistor? I mean, that sort of is implied, but again, specifically this type of component we are not using in our analysis up to this point. So that's another component which has an arrow, which is a potentiometer or a variable resistor. Okay. So are there any specific questions about the exam that you're unclear on, or any explanation that is needed for any of the problems?
No, I'm just not terribly confident with my techniques
Yeah,
at all. So
yeah,
it's easy to say, yeah, just pick whatever technique is easiest for you, but I don't.
yeah.
So
Let's
we'll
take,
see.
yeah.
I'm
Uh,
looking at the examples in the book too, and I don't know.
okay, so if you want to take a problem as a case study, we can discuss it, and maybe that sort of gives you some direction in approaching the problems of the exam. So um, if you are interested, I can do further explanation. If you feel like there's not sufficient information provided within that question, I mean, we can have a discussion on that as well.
Yeah, I don't know.
Okay. All right. No problem. All right. So
There's 4 questions and it's worth a lot of points. So that's the
yeah. So let me just quickly go and open the exam. Just give me a moment. Let me. Okay. So let me share. Okay. Since, as you mentioned, it is there are a lot of points associated, and it really has significant impact on the overall grade of students. So I'll spend a few moments on this, since I wanted to talk about the exam today. So if you look at the first problem, it's sort of similar problem that we saw earlier, where none of the resistors are in series or parallel combinations. So you can use that technique to simplify it to find the R total. In terms of the main current, main I, and total power, once you have simplified that circuit to a single resistor and voltage source, you can find the total current there, and you can find the total power there by the power dissipated by that particular resistor, since you know that the resistors are the power dissipated by resistor is a function of voltage and resistance. So I is equal to P is equal to V square or R. So you can use that technique. So P is equal to IV, and one of the I, then you can convert to I is equal to V over R, and that's, so I mean, that's just an interpretation of Watt's law. So that, just review that, and I should be able to find the power there. The second problem is saying that the current through RL is 40 milliampere. Use source transformation and calculate R sub L. Okay. So if you think about this, you are given current that is going through RL. And if you do, and also there's another process that is described to you. You have a 100 ohm resistor and a 10 volt source there. I'm talking about question number 2. And you can apply source transformation there to convert this voltage source into a current source. So then you will have essentially current coming from the current source, and you know the source current, and you can apply the current division technique at this point to determine what that value is. And once you know that, because since now normally what we do is we don't know the current in a branch and we know the resistance, In this case, it's opposite. So we know the source current, we know the current in the branch, but we do not know the resistance values. So since there's only one unknown in that equation, you can set up that equation to find your unknown value for the load resistor that way. So that's I mean, that's the problem which will basically test you on the techniques on how you can take the equivalent resistances, do source transformation, and also the current division. So that's sort of how your approach should be there. In the next problem, question number 3, it is just like the example that I showed you earlier. You have to find V sub x there, and V sub x, just a simple observation is that it is across 10 ohm resistor. So then what I need to do is I need to keep that 10 ohm resistor intact and not make it part of any equivalent network. On the right hand side of the 10 ohm resistor in the center, you see that there's a parallel combination of two 10 ohm resistors. You can combine them, then it's a series with the 20 ohm resistor. That's going to be your one side, one branch. On the other branch, if you want, you can then apply source transformation to combine the two resistors, and then again apply the source transformation, bring it back to a current source. So now you will have one current source and 3 branches of resistors, and apply the current division to find the current that is going to flow through that middle 10 ohm resistor. And once you do that, then you essentially should be able to find the voltage there. So then again, as I mentioned, you have all these inventory of different techniques. It's just that whatever is the suitable technique, you'll use it there. So just let me just okay, so what you would do is you will combine this, reduce the thickness, and then you apply source transformation here. It's converted to voltage source. You combine the two resistors, apply source transformation, bring it back to the to current source, and you have 3 branches. One branch is this one branch is this one, and then the third branch is going to be the combination of these 2 resistors. So, but again, it's going to be a single branch after you do that process twice. Source transformation to voltage source, back to current source, and you will have these 3, and then apply the current division. So that's going to be processed there. The last one is asking you to find I sub x. So if you apply the source transformation, and you have a current source on the right hand side, and with it is in parallel is the resistor. So that's an opportunity for you to think about, again, there's this direction provided there that how you should approach this problem. So once you have that, then you will have essentially 2 voltage sources within this circuit, and 2 resistors in series. So it's just a series circuit. So you combine the resistors, combine the voltage sources, and essentially you should be able to solve for I sub x there. So again, the main focus here is on source transformation, current division, and also the equivalent resistance value. Since I didn't include any nodal or mesh analysis problems in this exam because we had a dedicated homework assignment for that. So I thought, you've been tested on that. So therefore, I will not, I will use other techniques here. But again, between now and the due date of the exam, if you feel like you have any questions, you can still reach out to me. But again, I hope this helps you get some direction on how to solve this problem. Okay. All right. So in the next session, I want to, by the way, any questions about any of these 4 problems that, or if you haven't had a chance to look at it in detail more closely, then when you do so, you can share with me your questions, or if you know now, I can respond to your questions also.
Okay. No, I mean, I've been staring at it for a week now, and
okay.
it still terrifies me. So we'll see.
Oh, hopefully it helps. Today's session hopefully gave some relief. Hopefully. Now, regarding the lab component, let me share with you, and we'll spend more time. And in fact, what I'll do is, because my goal, since it's a very small class, I mean, just 2 students, and instead of covering a lot of material, I focus on whatever I cover, is retained. So you made a comment, a few weeks ago that the multisim that we use in digital course last term wasn't quite clear to you. So to remedy that, what I'm thinking is, just like in normal lab exercises, where you have a lab instructor which sort of walks you through the problem, and then we solve them together, and then of course you have questions. So what we'll do is we will use the next session to solve our lab problem in terms of simulation, and that hopefully would help you. You'll do the theoretical part just to verify your answers, but we'll do the lab component together. And for that, I would ask you to use the Multisim Live, which, let me share with you. Okay, so if you see this, it's www.multisim.com. So you'll go to this website, and what I would suggest before the next session to create an account there, and you can use your CTU email address to create that account, so that it is because they have sort of an academic relationship where the tool is available to students and the faculty without any charges. So maybe they ask you to, they send you verification code on that email address. So it's good to have the university email to register there. So please register there before our Thursday session, and then in our live session we'll work together. And I know that you are pretty good at taking notes, and pretty much you shared with me that. So and we'll work at a pace that is convenient. And I want you to get get a feel for this tool, because it's a very useful tool. You'll be using it in the future courses also, right? So I want you to take this with you to the next course. So when you're going to be taking your electronics courses or circuits 2 courses, any of the lab assignments, the multisim is a very useful tool for simulation of circuits. So I mean, last time I was kind of not sure how other students were keeping up with this, but you did mention that it was a little bit difficult for you to catch up. But now this time I'll make sure that we have it.
Yeah, so I'm able to go to Multisim Live and log in, and I've created an account, and I'm actually in it right now, so I am able to get in there for our next session, so I can
Okay.
figure that part out, because that was
That's-
kind of a key component that was kind of didn't let me get to the next step. So
Okay, yeah.
Multisim
That's
Live, I'm able to get into, have an account.
wonderful. Okay, so that's good to hear. You have access then, and we'll just go step by step in the next session, and create our circuit. And if you have opportunity, you can practice that. Maybe just create some circuit, find some values, etc. So, but I'll go in detail in the next session. Okay. So at this point, then I'll conclude the session, and we'll spend some time on the multisim next session. And if there's some time left, we'll move on to the next topic. But I intend to dedicate most of the time, allocate most of the time to multisim and the lab assignment in the next lecture. So if you don't have any other questions, I'm just going to conclude this session. And do let me know if you run into any roadblocks with the midterm exam. And I'm available on the messenger. So anytime you send, I should be able to respond to your question within a few hours. Just make sure you attach a screenshot if you have any specific question.
Okay, sounds good. Thank you.
Okay, thank you.